Much. Hey y'all, it's been a bit. How is it going? I can share for that prompt, something that made me happy today. It's getting a little cold here where I am, but that does mean I get to put sweaters on my dog, which is always big pro. He looks very, very handsome in them. How about you all? How's the week been? Anything that's been making you happy today?
Oh, I feel the same as Omar. I have a lot to do, a lot on my plate. It's been wild these days, actually. Yeah, I can handle it. I need to get some well-deserved rest and looking forward for this weekend.
Nice. All right, I see a couple other folks typing. I'll give everyone a sec. Thanks, Joseph. Appreciate it. Uh, all right. Well, hey, we have stuff to get into, but we're changing modules. A lot has happened. I think this lesson is pretty short as well, so you can decide if that's a great thing or excited for less time or very sad because it's less time with me. I know it's going to be really a downer for you all now that I'm just back. But I did kind of want to just check in and see how the past couple months go. I think last I left you all, I'm trying to remember what we were doing. I think we are doing DOM manipulation, sort of the basics of it. How has everything been? How are you all feeling about coding, React? You have this project coming up. What's going on? What are you all feeling? All right, Omar has given us a sassy gift, much appreciated. How about the rest of y'all? I promise I'm not asking just to bother you. There's good content to get to, but I just kind of wanted to do a pulse check of how folks are feeling. Here we go. We got that several people are typing.
Hey, Joseph and Tatiana are typing. I like that.
Something I appreciate the GIF. I feel maybe more confused now, but perhaps that's how you're feeling, which is why I want to share that. All right, all good. Well, again, I think today's gonna be pretty short. So we can just dive into it if that's easier. But I guess I'm wondering if there's anything that any questions you all have, you at a broader sense. I'll say, having taught a number of these classes, not necessarily with C1, but with other workers and things like that, the getting towards the end of the course is always really tiring for folks, right? You all have been learning so much. I'm sure your brains feel like they are overflowing with tons of content. Whatever I've always found, whatever the last thing is we teach, it's always the worst thing. I've tried reorganizing sort of the order of courses and be like, oh, well, we'll talk about this last. It's, just because at the very end, everyone's sort of topped up and full. Um, but yeah, is there anything that you all are wondering about large scale that I can I don't know, share with you? Any concerns or worries before we get into this next module? If not, that's okay. Just offering a free therapy session just before we dive in. But it's not for everyone. It's all good. All right, just got no concerns. Love that. Love that for you. Nice. Christopher sharing a project completed. Well done. All right. Well, excellent, y'all. Well, I hope you all are feeling, if not good, at least at a like you've learned a ton so far. So let me share a little bit about this module, and then we'll dive into the first lesson. So this module, actually, what is it called on your thing? Yeah, search and sort algorithms in JavaScript. This is pretty typical of a lot of these courses where at the very end we'll start to cover some computer science concepts. So I will say big pro here is that in terms of like really new technologies, we're done. You did it. You learned all the stuff you need to learn. We're not introducing a new framework like React. We're not introducing some new entirely part of the stack. So that is pretty exciting. Um, and everything we're going to be doing over the next few weeks is all going to be based in pretty basic JavaScript. So even new methods and things, we're not really going to be learning anything new like that. We're just relying on our JavaScript skills to solve some problems. So I certainly like that aspect of it. Not so much a con, maybe a neutral, is that the content we're going to be talking about for the next few weeks is, I would say actually the first week or so is going to be, I hope, pretty doable, pretty understandable. It's going to remind you of a lot of the code that we first started writing when we were working on JavaScript. As we get towards the end, though, it's definitely going to get tricky, and it's going to require you to really sort of bend your brain a little bit to think about problems in a different way. The importance of this module, I would say, is generally twofold. The first is that, well, I don't think you'll really be asked to implement any of these specific algorithms that we're going to cover on uh, an interview. It may happen, but I think it's actually pretty rare for someone to just say, "Hey, go ahead and spit out this algorithm." But the kind of thinking that you're going to do here is really important. And these concepts do come up pretty often on interviews, if not necessarily in coding, at least to be able to describe. So I would say the second important part about this is, as it sort of just said, this module is really about how do you think through problems. And we're going to cover some really common problems that computer scientists have tried to solve and have done so in a variety of different ways. So we're going to learn a lot of different sorting algorithms. Those are all ways to sort data. We're going to find out there's some benefits and cons to certain algorithms. And we're going to figure out how to implement those on our own. The good news is, in terms of memorizing those, you can always look them up. You can see them implemented in JavaScript, but also other languages. There's all kinds of different ways to continue to refresh your brain on these kinds of algorithms. This is the kind of thing that, as I'm preparing to teach it, and if I'm ever getting it for interviews, I kind of pour back through these to kind of make sure I'm up to date. It's an easy thing to sort of forget at a certain point. What I think is really great about this is we're going to get the opportunity to really drill down into a problem-solving process. And hopefully at this point, you all are feeling semi-solid on JavaScript, at least some of the basics. And so it means we're going to be able to apply those skills and really think through concretely, okay, how do I want to solve this problem? And what's like the best way to do so? So we're finally getting to the part of the program where we can start to really solidify our skills here and really concretely, critically think about problems using code now that we've had some practice with it. So that's the overall, I would say, purpose of this module. I hope that sounds interesting and or exciting. I do think a lot of this will be, if not exciting, at least like a little bit mind meldy and brain busting. It's some of these algorithms are quite fun. All right, let me go ahead and share my screen, and we will go ahead and get started today. All right, here we go. I also want to quickly ask, so I got a new microphone. Can everyone hear me okay? Does it need to be louder or, all right, thank you. Appreciate it. All right, so our plan today is to cover intro to algorithms and linear search. We'll see here, there's not too much to get through. I think as you all find, it's going to be pretty doable. So we'll spend a lot of the time talking about what an algorithm is, sort of walking through the process, talking about pseudocode, and then we'll end by wrapping up and completing our first algorithm, linear search. So our goal for today, our overview. So in this lesson, we're going to get an introduction to the concept of algorithms in programming. We're going to learn about linear search, a basic algorithm for searching elements in a data set. By the end of this lesson, we're hoping you're able to understand the fundamental concept of algorithms in programming, implement a linear search algorithm in JavaScript, and analyze the efficiency and limitations of linear search. That is the plan for today. All right, so first of all, what is an algorithm? So you all may be surprised to learn you've already been writing tons of algorithms as part of your course already. This video covers it. I'm gonna go ahead and play this. If you all cannot hear this, please do let me know in chat. I'll play this. If the sound's coming through weird or something like that, feel free to just mute me and then watch on your own. Give everyone a minute or two to watch this.
You may have heard the term algorithm recently, whether it was online or maybe in some conversation about technology. It's a word that gets thrown around a lot, but what exactly does it mean? Well, simply put, an algorithm is a set of steps used to complete a specific task. They're the building blocks for programming, and they allow things like computers, smartphones, and websites to function and make decisions. But in addition to being used by technology, a lot of things we do on a daily basis are also similar to algorithms. Let's say you want to make some spaghetti. In order to do this successfully, there's a certain set of steps you need to follow in a particular order. First, you need to boil a pot of water. Once it's boiling, you then add the spaghetti and cook it for a set amount of time, stirring occasionally. Once it's finished, you drain the water and then it's ready to be served with a sauce of your choice. That entire process is actually an algorithm. Because you followed those steps in that order, you reached your desired outcome, a delicious pasta dish. But if you were to make a mistake, say over or undercooking your noodles, it probably wouldn't be as good. Programs work in a similar way. Their code is made up of algorithms telling them what to do. Let's say that we want to use a navigation app to get directions. When we punch in a destination, the app uses an algorithm to look at the various available routes. Next, it uses a different algorithm to check the current traffic. And then a third one takes that information and calculates the best available route. All of these algorithms are built right into the app's code. If there were any kind of error in that code, the app wouldn't be able to follow these algorithms correctly, meaning you wouldn't receive your directions. Both of these examples show how both humans and computers can use algorithms to perform everyday tasks. The difference is that computers can use algorithms and calculate things better, faster, and more efficiently than we can. Technology is only going to continue to evolve and get even better at what it does. As long as coding and programming continue to be used, algorithms will be at the heart of these technologies, guiding what they do and how they do it.
All right, excellent. So we have here a description of an algorithm is a set of steps for accomplishing a task or solving a problem, and some details underneath. Let me ask you all, if you watched this video, but if you were trying to describe an algorithm to maybe a friend who's less technical or a parent, how would you summarize this? How would you wrap this up based on the video that we just watched? It might be putting together a metaphor or describing it in a more layperson way of terminology. What do y'all think? What would be a way you would describe an algorithm to someone who's not super technical? All right, we got the several people are typing. Excellent. Thank you, thank you. Excellent. So Omar said a set of instruction and steps to get to a specific result. Juan saying exact instructions on how to do something. Oh, does it scare off the rest of you? All right, Tuna says a chain of things to do to reach a specific goal. I like that. Nice. All right, excellent, y'all. Yeah, there's a couple important bits that you all are uh, pulling out of this, right? One is that we're following a set of instructions, we're following some sort of steps, and we're doing that to reach some goal. So there's an end state to an algorithm. That's a pretty important part of it as well. All right, so you all are very much right. So this diagram sort of very briefly sort of describes how an algorithm works. So the one thing that we didn't really see or maybe talk about as part of that last video was that one thing that could be an important aspect of an algorithm is the input to it. So the input can be, for example, on the previous algorithm in the video, maybe it's like what dish you want to make. It could be information about where you are currently, if you're thinking about a application that's helping you navigate or your destination overall. So you take that input. With that input, then you're going to pass it into your algorithm. As it says here, the algorithm, think of this as the brain or the engine of the process. This middle part represents the algorithm itself, a set of rules or steps that are followed to process the input. And these rules are designed to be precise and systematic to ensure that for any given input, the algorithm can produce the correct output. And that correct output is something we'll define, but the idea is given the input and running it through the steps we've defined, we're going to go ahead and get some kind of somewhat consistent output or somewhat expected output. And it says here, the output is usually the answer to a problem or the solution to a task. So there's a couple of qualities of algorithms that we want to keep in mind that would make them particularly effective. So one is that it should be finite. So an algorithm must always reach a conclusion after a finite number of steps. It cannot go on indefinitely. There must be a clear endpoint or condition that signifies completion. We've seen this, for example, when we've accidentally left open a loop or a while loop or something like that, where it just continually runs. The end goal, a good end goal of an algorithm is not necessarily running continuously. It's to hopefully do something for us, right? Ideally, algorithms are well defined, so each step of an algorithm must be precisely defined. The actions to be performed must be clearly and unambiguously specified for each possible input. And ideally, they should be effective, right? So an algorithm should correctly solve the problem it is designed to address. So for example, one of the examples in the previous video, if you opened up your Google Maps, your Apple Maps, your navigation tool and said, great, I want to go to this grocery store, and it sent back to you a funny meme. That's not what it's intended to do, right? We're not actually getting at the purpose of this application. So ideally, our algorithms, they do things we want them to do. They don't have necessarily unexpected results, even though the output might vary in terms of what the output could be. So those are three of the most common characteristics of effective algorithms. An example of this, particularly, I guess I'll just go back and just add a little bit more to this in terms of well-defined. Have you all ever seen those videos of it'll be like a kid describes how to make a peanut butter and jelly sandwich to their parent, and the parent takes it very literally and is like, putting peanut butters on like one part of the bread or not really following the fully, right, the spirit of the instructions. That's kind of the idea here, is that when we're writing an algorithm, and as you all have seen when writing code, you have to be very precise about exactly what's happening at every single step. All right, we have an example here. This is using sort of a flowchart kind of diagramming. And it's an example of an algorithm. I'm gonna give you all just like 30 seconds or so just to read this over before I start to describe it. See if you can follow what's happening in the flowchart. All right. I'll say, I think when I first looked at this, I was like, I feel like there's some squares missing maybe to this diagram, but it does make sense with these little steps over here. So let's walk through them real quickly. So we are starting an algorithm where the goal is to find the sum of 6 numbers. What this algorithm is telling us is that first we'll set some kind of variable, some kind of value of sum, set that equal to 0. And we'll do the same thing for a variable or a value called count and set that equal to 0. Great. Then we go ahead and enter some number. So that could be something like 1. Once we do, we increment sum by adding or reassigning it to itself plus that number we just entered. And we're increasing the count by 1. If the count is less than 6, we go back up here and we ask the user, hey, go and give me another number. We continue that process until count is no longer less than 6, at which point we print the sum and then the algorithm is over. So this is a pretty straightforward algorithm in terms of, maybe you all can sort of imagine how you might write something like this in JavaScript. If you look down here, there's a few different reasons why this ends up being an effective algorithm. So first of all, it is finite. This process will stop at a certain point, right? It does not go on forever. It's not just consistently summing numbers, and has sort of a clear point at which it will end. It's well defined. Each step of the process is outlined and leaves little room for ambiguity. And we can see that up here in terms of what exactly is defined and what is being asked of the user in terms of the input. And then it's effective as well because we wanted to calculate the sum of 6 numbers, and it is going to do that, right? It is going to solve that problem for us. So it is indeed solving a problem we've defined. All right, actually, before I move on there, any questions about this or algorithms in general, just before I move ahead? Pretty, is everyone like waiting for the shoe to drop for it to get more complicated? This is really just it. When we talk about algorithms, I think folks get a little overcomplicated about it, talking about like really complex algorithms. And there are, of course, complex algorithms. When we're talking about just the term, we're just talking about a series of steps. And again, you all have built tons of algorithms. Anytime you've written a function, that is essentially an algorithm, right? So you all have already worked with this, even though terminology may feel slightly new. This is something you all are quite familiar with at this point. All right, so there's all kinds of algorithms out there. You all have written plenty of them. There are some common types that we'll see over the course of the next few weeks, and that if you were to search around online, you might find some of these as well. So one of the most common types of algorithms is search algorithms. These algorithms are used to locate specific data among a collection of data. This includes linear search, which we'll talk about today. It includes other types of search as well. Sorting algorithms will help you to organize data in a specific order. Common examples include bubble sort, quick sort, merge sort, insertion sort, selection sort. We're going to talk about all those different ones soon enough. The goal there is, for example, take an array of numbers that are unordered and make them ordered in some way. But it could also be taking an array of objects and reordering them so that they're all ordered by a particular property. We also have recursive algorithms. So these algorithms solve problems by solving smaller instances of the same problem. So recursion is often used in divide and conquer strategies such as merge sort or quick sort. Another classic example is the calculation of Fibonacci numbers. So we'll talk about recursion at some point as well. And it's sort of like a little bit of like a fancy trick that computer scientists can do, and a nice way to think about certain types of problems that have repeating structures. There's dynamic programming algorithms. So these are used for optimization. So dynamic programming algorithms break down a problem into simpler subproblems and store the results of these subproblems to avoid computing the same results multiple times. I don't believe we'll be covering any dynamic programming algorithms specifically in this course, but these are some of the most interesting and I would say many times most difficult to learn, but also can be really powerful to solve certain types of problems. And then finally, we have graph algorithms. We'll be covering graphs in this course, but graphs are actually a really important way that a lot of technology works. It's a data structure and algorithms that can traverse this data structure, find information within it, connect different points would be considered graph algorithms. There's a number of specific ones, just specific to graphs. So each category of algorithm has its unique applications and is chosen based on the problem constraints and requirements such as time complexity and space complexity. We will talk about that all soon. One thing I also want to note here before we move on is I guess actually two things. So one is we have in this course, whenever we've needed to do something, perform some kind of operation, we've taken a look at the JavaScript language and reached for, hey, what does this language provide that we can use to solve this kind of problem? You can think of that when we were learning loops, right? So we talked about loops in terms of, hey, we need to perform this operation or set of operations multiple times. What tools can help us do this, right? So we reached for a for loop. These type of algorithms work kind of in the same way. Once we know about them, the idea is, oh, I need to search through this kind of ordered list. I'm going to go ahead and reach for this particular searching algorithm. In order to do that, sometimes these things are built in for us. So for example, for linear search, as we'll see, we've already done linear search a number of times. There are also some methods like in JavaScript.find, which can help us do something very similar to some of these algorithms. The reason we're learning these and sort of writing them out is, again, the purpose here is to be able to understand what the algorithm does. As we're going to talk about later, we'll talk about the efficiency of algorithms. This is really a tool for us to better engage with different aspects of coding. These algorithms can show up in all different languages, all different programming languages, whereas a specific method, something like .find, may look different or not exist in other programming languages. So that's just a little bit of the difference here, right? Is that we're talking here about concepts. We're going to implement them in JavaScript, but these are concepts that we can take to all other programming languages and a lot of other different concepts that we have. So I just want to make sure you all know that. And again, we can always look these up. So in terms of understanding it for an interview, it's going to be a little bit different. But when I'm talking about like you're on the job and you're trying to figure out what's the best way to sort some different data you have, these are things that are well established. So we want to be curious about how they work, but there is a solution that exists that we can always take a look at. And there's some variation in those solutions as well. All right, we've moved on from our intro part, and now we're just going to talk about searching and linear search. I think this part will feel nice. I hope it'll feel nice for y'all. All right, so what's searching? So searching means looking for something, right? We're looking for a specific item among a group of items. So linear search is the simplest, most straightforward algorithm for finding a specific value amongst many different values. Our algorithm is going to check each value and compare it to the value it's looking for. The value it is looking for, that's going to be our input. The part of the algorithm that works, right, is taking in the target as well as some data, searching through, and then we'll get a result back depending on whether or not that data we're searching for is within the overall data collection. So let's take an example here of an array. So we have here an array of numbers. They're not ordered in any particular way. They're just unordered random numbers. The description here says items stored in an array have a sequential relationship. To dive into that, and you all will remember this, what that means is every spot in an array has a label associated with it. First spot with location is always labeled 0, so on and so forth. We've talked about indexes. You're hopefully this is coming back. I guess let me check. Does this feel familiar? I know you've all been talking about like UX, UI. Are we comfortable with indexes at this point? I don't want to assume anything. Tina says, rings a bell. Yeah, sounds somewhat familiar. All right, excellent. Yeah, so hopefully this doesn't feel too scary at the very start, right? We have an array of these 6 numbers. We use zero-based indexing. First number is going to be at index 0, and it goes up to 5. The length of this array is 6 different numbers, right? 6 different values. So each of these indices allow us to go through each item in an array one by one. So what that means is we can step through our array. And again, right now we're talking about array, and I'm sure the first thing you're thinking of is array brackets, right, in JavaScript. But again, this could technically be any kind of collection that has a sequential order. And there are other types of collections that have sequential orders. In this case, we can just think about working on an array. Our goal, what this algorithm is going to do is we're going to take in some number, and then we're going to start at the very beginning, and we're going to step our way slowly through until we find that target number. That's one option of what could happen. This shows that example. So here we're using linear search, to check if 9 is in the following list. So we would start at 1. Is 1 equal to 9? Nope. Move on to the next one. Is 7 equal to 9? Nope. Move on to the next one. Is 2 equal to 9? Nope. Move on to the next one. Is 9 equal to 9? Yes, it is. Once we find that, in general, again, the overall algorithm is just about searching and finding. You could really return whatever you want. Typically, we would either return back true, as in, yes, this value is within this list, or we would return the index that the value is at, right? So we could either return true, or we could return the index of 3. I'm right back. The little guy was creeping me out. Hello, hello. It's just staring at my soul. All right, if we were searching for a value of 8, in this case, right, the 8 is not in here. Now, as humans, we can just take a look at this and quickly scan and go, great, it's not in there. But we have to tell our computers really concretely what to do. And so it's going to step through every single item in this list, and then it would not find the actual element within there, right? It's not going to find the value of 8. In that case, we have an option. We can return back false. If you all have used the index of method anytime recently, you'll know it returns -1 as an index if the value is not found. Kind of depends on how we want to represent not found. Actually, let me go back here. Any questions on this? That's it. That's linear search. You all computer scientists, we're good to go. Let's hype ourselves up. Feeling good, right? That's our first algorithm. Yeah, exactly. Raise the roof. Love it. So this is pretty straightforward, right? This is nice. But this is an algorithm. We did this probably the first, I want to say when we learned for loops. I forget if it was the first, second day. We started iterating over arrays and collections, stuff like that. But this is pretty straightforward, right? Which is really nice. So this algorithm, its only job, right, is to find whether or not the given value is within the given array. If it is, we want to return something affirmative. If it's not, we want to return something negative. That's it. All right, so now I'm going to ask you a couple questions about linear search, and we can sort of think about how this applies overall. So first of all, given this list, how many comparisons would you need to do in order to find the element with a value of 56? So I want to know how many comparisons would you need to do in order to find the element with a value of 56? What do you all think? Ooh, Juan's getting smart with this. I like it. I like that you're anticipating my next question. Excellent. Yeah, so 4, right? We need to first compare this first value here. Second, compare this second value here. Third value, fourth value. So a comparison. And We're going to check that 56 is equal to 56. At this point, we return back something like true. We return back the index of 3, whatever we want. Interesting to note, if we went from the right side, we instead linear searched from the end to the front, we would only make 3 comparisons. We would check 70, we would check 3, we would check 56. All right, just keep that in there. Just as a interesting. All right, given this list, how many comparisons would you need to do in order to find an element with a value of 45? How many comparisons would you need to do in order to find an element with a value of 45? Yeah, excellent, y'all. Right, we need to look through the entire thing because it's not there. So we would start at the beginning, check 11, check 64, check 27, et cetera, and we keep it going until the very end. Even if we start from the right, it would be the same number of comparisons. Only once we've traversed through the entire array would we have a sense that, nope, this number is not within this data structure. So let me ask you all a question. Well, do you all remember the constraints that we had on this array? What needs to be true about this array for linear search to work? Let me put it that way. What needs to be true about this array? What are true facts about this array in order for linear search to work? And that's a bit of an odd question. First of one says the thing we are looking for must be there. We actually just saw an example, right, where the number we were looking for wasn't there. So it's actually okay. If it's not there, that's fine. We can still perform linear search, although I know what you mean, right? Ideally, it's there. But we can't actually ignore it. Just as saying indexes, yeah. So one constraint, just to, we're kind of pulling back here. One is that we need some way to iterate through the data structure. I know we're thinking just like JavaScript array, right? And so we're stuck there. But again, in other languages, we may have a different type of data structure. In JavaScript, we could have a different type of data structure. But we need some way to be able to iterate through. If we had a linked list, which is a data structure, we wouldn't necessarily, we could kind of have indexes, but we might just have a way to sort of move forward consistently. So there are other type of data structures we need to keep in mind. Cool. I think it's pretty good. There's probably a couple other constraints here. So one is, what do you all think about handling an empty array? What's the right way to handle something like that? We're assuming we're passing in a data structure that has data in it. But what if we're looking for the number 9 in an empty array? How do you all think we should handle that? You can just program an algorithm to just like respond, what the hell, man? Give me numbers. Give me something in the array, right? All right, I got some slight agreement on that one. So when we're thinking about an algorithm in general, this is kind of like a little bit of an edge case. And so bringing this up now, in our case, this will be easy to solve. But in other algorithms, this could be a bit more complex, thinking around, okay, well, some of our assumptions are there's actually data in here. It's sequential in some way. We can go forward or backwards or something, right? But what happens if there's actually no data? How do we want to handle that, right? So in the case of linear search, how it's typically handled is that we would say, well, if the list is empty, then the number we're searching for, the value we're searching for, is not within it. So however we typically will respond in the negative, that's how we're going to respond. So that could be responding with false, with a -1, right? We're saying, well, there's nothing, so there can't be anything in there, right? That's typically how this is handled. But this kind of scenario will show up in a number of different algorithms. We have to sort of consider what happens if the data structure is empty, what happens if the input's empty, right? You all have seen this plenty. One thing I just want to note, because we will talk, I believe, about binary search tomorrow, is that this list, while it needs to be sequential, the numbers do not need to be sorted. The values in here do not need to be sorted. right? So you can see we bounce around here in terms of the value order. It's just that we need to be able to somehow iterate through the data structure. So linear search is quite flexible in terms of we just need some sequential data and then we can search through it. All right, so that's linear search. Hopefully it doesn't feel too stressful. Next thing we're gonna talk about is pseudocode. We talked about pseudocode before, I think a few different times. We're sort of revisit it here. We'll add a few new tools, and then we'll continue on. So as you all have seen, pseudocode is a tool used to design algorithms, combining natural language and the basic structure of code to outline a program's logic without focusing on syntax specific to any programming language. It helps programmers plan and communicate complex ideas, simply focusing on the algorithm steps rather than technical details. I know that I was trying to force you all to do this. And I know sometimes when it feels like, oh, I kind of know how it works, it's easier just to start typing out code, right? But I really want you all, and you're going to see it's going to feel really necessary as we move into some more complex algorithms to really be thinking about what the steps are before we actually write out the code. So this is an important skill we want folks to be able to do as software developers, particularly when you're communicating with other developers or just trying to figure out an idea and not have to wrestle with, I'm trying to solve a problem and I'm trying to remember what was that JavaScript method that did the specific thing, right? We just want a way to sort of talk about the problem we're trying to solve. So I'll say, I think this is really actually interesting, the content they've added in here. In general, I've seen pseudocode written a lot of different ways. And there's not like a canonically right way. I like how they have it here. So we'll go through that, but there is, I think, a little bit of flexibility here in how you want to communicate your ideas around an algorithm. So there's 6 programming constructs. And as we'll see, this is often written in uppercase. So a sequence represents linear tasks sequentially performed one after the other. We use the word while to represent a while loop. We'll use repeat until as some loop that has a condition at the bottom. For, another way of just saying for looping. If then else, these are terms we know, we would write them like this to signify that we're doing some sort of conditional statements. And then a case statement would be something just like in JavaScript. We would write in where there's perhaps a number of conditions based on some certain value. So these constructs are really just sort of like categorizations of how we want to write certain ideas. Again, I know it can be a little bit weird sometimes to think about how does this differ from JavaScript? I think JavaScript, thankfully, just uses a lot of these words to communicate these ideas. But there are some differences. So for example, over in the sequence construct, for initializing a value, it suggests using the word set or init as a way of declaring that. In JavaScript, you all know we use let or const, right? That's our syntax version of saying, hey, this thing's a variable. When we're writing pseudocode, we might say set this value equal to something else. That is, I think that's maybe the most interesting bit in here. All right. Cool. Yeah, we have an example here. All right, so these are some simple steps. Again, I will say I've seen this pretty flexibly adhered to. So I would not stress too much about memorizing every single word on that previous page, so much as understanding the idea of what we're trying to communicate. So in general, we want to capitalize the initial word and other main constructs. Remember, we're trying to use a word that conveys a specific technical idea. We'll try and capitalize it. We're going to make one statement per line. We're going to indent to show hierarchy, improve readability, and show nested constructs. We'll end our multi-line sections using any of the end keywords. And so what that means is, and we'll see an example in just a moment, but if we're going to do an if statement, we might have an if statement, maybe an else, and we say end if. This is just a way of writing to make it clear for folks reading when this starts and ends. We'll keep our statements programming language independent. So the goal of pseudocode is not to do things like actually saying dot filter or dot map. You might say map through the values to do X, something like that. Use terminology from the problem domain, not that of the implementation. For instance, say append the last name to the first name instead of name equals first plus last. So again, we're trying to describe what it is we're doing. And then ideally, after all those rules, keep it simple, right? Concise and readable. So we're trying to find a middle ground between writing the actual code and writing a paragraph statement about how we feel about writing this algorithm and its intended goals, right? We're trying to find some middle ground between those. So here's an example of what some pseudocode might look like. So here we're setting the move count to 1. The idea here is that we're saying, okay, there's some variable. We're going to set it equal to the value 1. Notice we're not saying let set count equal 1. And we're saying for each row on the board, and then for each column on the board, if game board position, this would be row and column, is occupied, then call find adjacent tiles with the specific row and column and increment move count. So the idea here is we're setting up our for loop for each row of the board. We're setting up our for loop for each column of the board, and then performing a conditional statement here if that game board position is occupied. This is sort of a searching algorithm to find adjacent spaces around a particular spot. So notice the language here is pretty readable in the sense that we're saying, okay, well, if the game board's position is occupied, then go ahead and call, I would assume this would be a function with some values and increment the move count. The things we're capitalizing here is really, again, just for us to see and hopefully be able to identify, okay, these are some important decision points, constructs that are stepping out that we'll need to implement into JavaScript. Notice as well that a lot of these ideas are not really well defined. It's much more about the concept. So when it says for each row on the board, for each column on the board, we don't know what data structure that is, how the board has been implemented. Is it an object? Is it an array? We're not actually worried about those implementation details. We're just trying to get at the concept here. We're just trying to get the idea of what it is we're trying to do. So with pseudocode, you can be a little bit loose. You don't have to define every single thing as you would with code, but you want to make sure the idea feels pretty clear at the end of the day. All right, any questions on this? Nah. Good to know, Omar. I'm sorry for your loss. That sounds stressful. All right. So let's go ahead and do our example with linear search. All right, so we talked about how we want to write pseudocode out, and then we have linear search we've just talked about. Let's combine these two ideas and go ahead and write out some pseudocode for linear search. So what I want you all to do actually is go ahead and try this first just on your own. We'll come back together and talk about some different solutions, but let's give you all, we'll say 3 minutes or so, and 3 or 4 minutes, and just try and stumble your way through writing this out. Again, you can use, and I would encourage you all to use some of the, sorry, going back here, the constructs right here of trying to use maybe the words like set or, while, repeat, et cetera, et cetera. Start with trying to use those. But again, we're just trying to find a way to explain this algorithm without relying on specific technical syntax or JavaScript, right? That's the distinction we're trying to make here. So let's give you all a few minutes. We'll say 3.5 minutes, and then we'll come back and we'll talk about a solution. All right, how'd it go? Anything interesting, challenging, exciting, easy, horrible? Anything? Any reactions? Still working on it. All right, fair enough. Yeah, take some time. All right, how about the rest of you all? Joseph, Timo, sorry, Abbas, God's World, Tatiana. Feeling good? All right, folks still working on it. We'll give you another minute or two then. All right, still working on it. That's a-okay. I'm just going to start to talk through it, and we'll catch up when we can. So I think there's a couple ways you could start with a problem like this. Assuming we generally understand how linear search works, the first thing we might do is maybe just like write out kind of like our own little kind of mission statement for this, right? So we can say something like linear search is designed to take in a collection of values and a target value and determine, no wrapping on this. Let's wrap that down. And determine whether or not that target value is within the collection. So something like this can be helpful just to kind of help remind us where we're going at the end of the day. We have some of the guidelines over here of what we're trying to do. And the great thing about this is there's lots of right answers. There's the only wrong answer is writing out code explicitly or staying at this level, right? So what can we do? Well, we know we need to somehow talk about the fact that there's some collection, there's some target value that we want to search through it, right? So a couple different ways we can do that. We'll look at the solution that's in here in just a bit. We can talk through that. I'll doing this a little bit different. So we might say something like set or maybe initialize, they had the word init, collection and target value. You could use it just like language, or you could write it just like regular language. If it's easier to parse, to kind of turn it into some kind of variable, something like with snake case or something like this, that's fine too. Whatever it's going to be, again, be easiest to read, but it's still pretty system agnostic. It's not really specific to a particular language. So we might say, okay, if we have a collection and if we have a target value, I say for every value in the collection, notice I'm not writing for let I equals 0 collection.length, anything like that, right? I'm just saying in general, if I'm saying this out loud, for every value in the collection, I want to do something. So we're gonna have more sequence here. Before I move forward, I'm gonna say end for. This is us saying this is the entire block here. This is when this for loop ends. We don't have in pseudocode the curly braces because that's system specific, right? So in this case, we're trying to make it really clear when some part of our statement starts and when it ends. So for every value in the collection, if current value equals target value, maybe I could make this even more Englishy. If the current value equals the target value, then do something. I'm going to add my end if statement right here, right, to let us know where we're opening and closing. So if the current value equals target value, then maybe we would do something like log out, because what does it say over here? So your pseudocode should indicate that the value is found and at which position on the list. You can say something like value found at, we could do something like at current index, something like this, sort of signify what we're getting at here. This is maybe getting a little bit language specific, but I think this gets at the idea without adding string interpolation, something like that, which would be very JavaScript specific, right? We could also do something like just saying value found, and maybe we return and end. If the value is not found, what do we do here, right? So a couple ways we could do this. We could say if all that runs and nothing happens, then we might say if value not found, do my end if, go ahead and log value not found, return false. You see I'm already turning this into JavaScript just out of habit. Maybe it looks something like this. I think this would be a fine way to write some pseudocode for this. The sample answer down here is a little bit different. So I wanted to show you all a couple different options here. So I'll say that's one option. I like this one too. So this one starts with a for loop, which says for each value in the array. Notice we're kind of just skipping over whether we want to define collection or target value. Depending on the algorithm you're writing, it might make just as much sense to do that and really describe this out. So for each value in the array, if the current value is equal to the target value, this is getting a little bit specific, perhaps into a syntax, but a lot of languages use equal signs to mean just that. So perhaps it's okay for our use cases. If the current value is equal to the target value, log target found and return the current index. Otherwise, the current index equals the last index of the array. So there's not necessarily like a exact correlation to JavaScript here, but we have the idea, right? If we reach the end of the array, then go ahead and log target not found and return false. I think both of these are perfectly fine ways to do this. Awesome. Thanks for sharing that, Joseph. Appreciate the solution there. Any questions? Any questions on this? All right. It's pretty loose. It's pretty loosey goosey. The thing we're trying to avoid again is being too prescriptive with our language of choice, while also making it clear what exactly is going to happen at each step. There's probably always more precision we're going to be able to add to pseudocode. But again, at a certain point, we're starting just to get into the implementation details. And so it's, there's a little bit of an art here to being able to write it out. Omar, you can ask, in your example, the end for shouldn't be at the end. To mean this one? You're saying like down here, right? Yeah, so in this case, my for loop is just this part, and then it's saying like afterwards, after you run that, go ahead and run this check. Right. Any other questions? Thoughts, feelings? No thoughts, just vibes. All right, I get it. I get how it goes. All right, excellent. All right, we're at our break. I think that's a good time to take a break. That works for me. So let's take our 10-minute break. When we come back, we'll actually implement linear search now in JavaScript. Let's talk about some additional steps that you all can get started with to improve your algorithms and problem solving. And we'll see if there's anything else we can discuss that might help you all out before we close out for the day. So see you all in about 10 minutes or so. All right. Hello. Welcome back, y'all. How was your break? Did you do anything nice?
It was a
Nice for
nice
yourself?
break. Good music. I don't know
Oh.
who's the DJ.
Great DJ. Excellent DJ. Kudos to the DJ. All right. I'll share my screen. There we go. All right, excellent. Let's do linear search, shall we? Let's make it happen. All right, so the plan now is we're going to write out our actual algorithm in JavaScript. We have the sort of basics right here. I'll talk through this in just a second. And of course, we also have our pseudocode as well. So a good step actually might be to pull over whatever your solution is. Plug it into your script file and then just go ahead and comment it out so you have that to reference. That could be a helpful thing to do. So for linear search, the plan is we're going to implement a function called linear search. And take two parameters. It's take an array, for example, with the parameter name of ARR, and a value to search for, which could be a target. Function should iterate through the array and return the index of the array. The index of the target if it is found. If the target is not found in the array, the function should return -1. Remember to figure out some way to handle an empty array in a manner of your choosing. There's a couple different ways you could do this. Once you're done with that function, they're going to test your function out with at least 3 test cases. You're going to search for a value that exists in the array. You're going to search for a value that does not exist in the array, and you're going to search within using an empty array. So you want to test at least those different options. Any questions on this before we get started? All right. Maybe it's been a bit. I know you've been doing UI UX stuff, right? So maybe you're more with those fingers. Let's take 10 minutes or so to do this. If you get to a solution though, please do let me know in chat so I can help gauge where everyone is at. So again, we're just writing the linear search function. Go ahead and give that a shot. Once it seems like folks are on a good path, we'll come back together and I'll help implement it with you all. All right, see you all in just a few. So maybe we could just add like 9 minutes onto the timer. Does that sound good? All right, sick. All right, how's it going, y'all? How was linear search?
How was it?
Almost
Almost
done.
completed. Nice.
How did everyone else do on the call? Done? Working on it? Not good? Somewhere in between? Thumbs up from Joseph. Appreciate it, Joseph. All right, I'll go ahead and share my screen. We can walk through a solution. All right, there we go. All right, so for linear search, right, we're going to write a function. Name linear search takes two parameters, an array and a value to search for targets. Let's go ahead and start with that first step here. So in JavaScript, I'll go ahead and define a function called linear search. We'll add those two parameters, and then we have room for our function body. I'm actually going to go down here and just go ahead and put together our test cases as in advance so we can start to run it as we start to walk through and see how this sort of shapes up as we build out the function. So I might say array one, actually we'll just say array. Let's pick some numbers in here. Excellent. And then we could say console.log. Isn't like success case? I'll say linear search. Array will pick a number within there, which is 0. I'll say unsuccessful case. Linear search array. Try and search for number 10. And then we'll say empty array. I'll pass an empty array there and go ahead and take a look for a number. Okay. Let me space this out a little bit, spell some of these words correctly. There we go. All right, when I run this code, what do you expect to happen? Have an idea, think in your brain, think it's gonna happen. Yeah, this makes sense. We haven't written any code, right? We just wrote the function. Perfect. All right, so let's go ahead and write out that function. So remember, our function should iterate through the array and return the index of the target if it is found. Excellent. Let's focus on that first. So in this case, there's lots of different ways we can loop over stuff, right? Let's stick with our classic for loop. For let I equals 0, while I is less than array.length I plus plus. Then here, we want to do some kind of checks. Right now, if we look at our pseudocode, we're initializing our collection target value. We have those up here. For every value in the collection, all right, we're starting to do that. I'll go ahead and just grab out the value here. I'll say array at I, right? So now we're accessing each value within there. If the current value equals the target value, so if value equals target, then we want to, in this case, the instructions previously were like return index, log something out. We have something more specific here, which is to return the index, right? So we can return I. All right, let's run our code. We haven't accounted for every case. Let's run our code and see what happens. Cool. Seems good. Our algorithm's starting to work, right? So here we have our index that we're getting in our success case. We change this value around, but continue to keep the success case true, right? We want to look for a value that's within that array. We can indeed find that it works. Okay, not bad. All right, now we need to do something where we account for the fact that if it was not found, then we want to return -1. So what can we do? So here, if we look at our pseudocode, we're saying if the value is not found, in this case, log value not found, return false. We want to return -1. Well, some of the pseudocode is actually sort of implicitly included in the code that's already been written here. So what we're saying here is for let I equal 0, yada, yada, yada. If we return, that's done, right? That means we found it. So that is kind of our if statement. If we get to this point in the code, we already know we haven't found the value. So at that point, then we can just return the value that we're looking for. So we return -1. Let's see if that works. All right, excellent. So in this case, we actually solved both our cases, the unsuccessful case and the empty array case, in the same way. It says here to remember to handle an empty array in the manner of your choosing. So right now it's just returning -1 because the array is empty and we're not able to find whatever value we search for within that empty array. If we wanted to do something different, maybe we could do something like if array.length is 0, maybe we return something like false. We could return array cannot be empty, right? There's all kinds of different things we could do if you want to update that to be slightly different. So lots of different options here. There's a sample solution down here as well. Just take a look at that. This one matches that pseudocode that they put together that's as part of the sample earlier on. And you can see here they're doing a check first to see if the array length doesn't exist in this case, where it is 0. And then looping through, and as we're looping through, returning if the values match, or if the array, if I gets to the last index of that array, then returning -1. So lots of ways to implement linear search. All right, any questions on this? Should I get something similar, something different? All right, how about this? What are we feeling in terms of difficulty so far? Anything unclear still? Anything not sure how I got to a particular solution? All right. Whoa, Omar, search for complicated values. Love it. Thank you. All right, Joseph says good so far. Okay. If we take a look at the code that was written here, or even the code that's in this sample solution, right? This matches up with our pseudocode. This is also code that we've written before, right? We've written this kind of code where we've searched through an array for some kind of specific value. We've done iteration before. We've done these kind of checks to see whether or not an array is empty or that a certain value exists, right? And we know about return orders as well. That return will end the invocation of a function. So we've seen this all before. We're now just sort of giving it a name, right? We're wrapping it up in a particular package and saying, great, this is linear search. All right, that is basically the end here. So let me point out a couple of the things that you all can do to continue working on algorithms. So first of all, there is an optional practice here. This is on a website called Geeks for Geeks. They have a bunch of different problem-solving challenges. You all can log in, it's not too hard, and solve this. This kind of interface is very similar to if you were applying for a software engineering job. You would maybe work in something like this to solve a problem that the company has sent to you. So even if this was easy or like straightforward, this is a good experience to have because it mirrors the experience of what you might get as part of a software engineering interview. I'll also remind you all, I must sound like a broken record now, but you all can also always use Code Wars. I would say now is the perfect time. If you haven't really picked this up yet, or you've been a little bit afraid of it, now is the perfect time to start getting involved with websites like this to practice your algorithm skills. So remember, you can log into Code Wars, you can go over to practice, and then you can pick out a specific challenge within here. All of these challenges you can sort by lots of different, categories here. You could pick the easiest ones first, or get feel familiar with the platform before getting to some of the harder ones. You all should have these skills now to work on many of these. And as we're starting to work on these algorithms, again, we're not necessarily learning anything new. We're going to repackage up some of the content we've learned already. There are a couple new ideas, but even that could be implemented with what we've learned so far. I think this is a great time to begin practicing here. Last little bit just to recap here in terms of what we talked about today. So again, we talked about algorithms overall, what they are, how we define them, where that algorithms is really just describing a sequence of instructions. Any function that you all write, that's going to be an algorithm. Algorithms should have an input. They'll often have an input. They should have some kind of output, right? We're trying to accomplish some kind of clear tasks. And there are a number of ways to build effective algorithms. That includes making sure that they don't go on forever, right? They don't have an infinite loop, that they do indeed get to the end result that we want, and that the instructions are clear and precise. We use algorithms in our day-to-day, even though we don't think about them as algorithms, right? Any process you all have that you repeat, whether you put water on the toothbrush before or after, right? Or maybe how you start up your car. Those are all things that we sort of in our head, we have habits around this. Algorithms is just a fancy word for us saying we're going to codify this in a way that other folks can understand it. And we're going to eventually turn it into some kind of program to be worked with on a computer. So pretty, I think, straightforward concept. Of course, as we continue to work on these more challenging algorithms, as we'll see, there are a lot of tricky ones that perform some really interesting operations, but will require some work to understand. So that is our lesson for today. Any questions? Folks are feeling good. Excellent. There's no really additional work here. We have some optional challenges, but you all have your project, I believe, that you're still working on, right? Seems good. Okay. Are there any questions from any previous projects that you all have worked on that you're still struggling with? So from what I hear, projects 9 and 10 are pretty challenging. Any lingering questions there that are coming up? If it would be helpful, I'd be happy to go over one of those in a future lesson if we have some additional time. Is there anything that you all would like more review on, as the latter half of this module, I think might be a bit busier, but I think the first few lessons here will have a little bit of extra time. So are there any of the projects or any concepts in particular you all would like a bit more practice with and or a bit more explanation on? I can just pick stuff out randomly, but I don't really need to talk about code as much as you all need to learn code. But I like it. I could just start, pontificating about stuff. Dan, this says it'd be great help. Awesome. Yeah. Are there anything in particular? Which projects are you all struggling with the most? Which ones feel the most confusing? What do you all think? You have a couple over here. Let's say project 9. Oh, that's supplemental material. Let me not open up that one. Yeah, okay. Any of these in particular? So we had, looks like project 8 was a recipe sharing platform. Do I remember this? I think I do. Some of these I worked on and others I have never taught, so it's always exciting to look at some of the projects. We had the data gallery app as well. This was with React making external API calls, it looks like. Module 10 was contact list app. Any of these seem interesting to go over?
I think I can launch a poll tomorrow to know which of these assignments maybe are the most challenging and share the results with you.
Okay, we can do that too. Excellent. All right, in the meantime, if there's anything that you all think of that would be helpful for me to cover, please just let me know. We can always try and figure out time and set aside to go over that. I think with that, I won't belabor the point. We have some extra time here, so I would recommend I guess two things. One, keep working on your project, right? So if you're working on that, that's a high priority. And then if this is still feeling maybe a little confusing, or even if it's feeling good, start to take a look at those other websites like Code Wars, Geek for Geeks, and just try out, start with some of the easier problems. There's not going to be easy, they're the easier problems, right? But just to get comfortable with some of the tooling there, because that'll definitely be helpful moving forward and getting into that brain space of, okay, let me read through a problem. How do I start to put together some pseudocode for it? How do I go ahead and solve it with JavaScript? That can be a really good process to get some practice with. It'd be really essential for software development interviews for sure. Okay, I'll stop there. Thanks for chatting with me about intro to algorithms and all that. It was good to see you all. It's been a bit. I hope you all are doing well.